So today I will be talking about traversable wormholes and some relationship to quantum teleportation. And connection to quantum teleportation. And the initial paper on this was a paper by Gao, Jefferson, and Wall. And then we wrote a paper with Stanford and Young, and then there are some other related papers by Hayden and Preskill and Susskind and Shao. So I'll discuss some of those things. Okay, so why are we interested in this? The motivation is that these ideas are some way to explore the interior of the black hole and some perhaps more sharp way to connect entanglement and wormholes. So, before we just, so I'll try to describe the relationship. So first I like to, before we go into wormholes and so on, I'd like to say a few words about ordinary quantum teleportation. So we're going to discuss quantum teleportation. So there is this Star Trek teleportation, is that you walk in somewhere and then magically you appear somewhere else very quickly. Right? Of course, the laws of physics require you to transfer information only at the speed of light. Right? So quantum teleportation is a situation where you take a qubit and you send classical information, and then the qubit appears somewhere else. So instead of sending the full quantum information, you only need to send classical information. Now this at first sight seems hard because if you think about a qubit, so a qubit, let's say in a pure state, has in order to specify it completely, you need to give the direction, let's say where it has the spin set projection equal to plus 1, right? So a pure state for a qubit is just a spin pointing in some direction, right? And so you need to specify the direction. That's an infinite number of variables, an infinite number of bits. I mean, it's two continuous variables, so you need an infinite number of bits to specify it. But nevertheless, through teleportation, you can send this with just two classical bits. Of course, the trick for teleportation is that that's not the only resource you need. So the resources that you need is that first, you have to share one entangled qubit. So the proverbial Alice and Bob. So we have here Alice and Bob, and they need to share to have arranged, to have transported in the very far past one entangled qubit. Okay. This qubit contains no information. It's completely unrelated to the qubit that we want to send. And then the second resource is that we need to send two classical bits, 2 bits, ordinary bits of information. So this Alice will do some operation, and we'll specify the operation in a second. And then she will send 2 classical bits. So this is one entangled qubit. And then Bob will do something and will get the message. So there is forgot to mention, there is the message qubit that you want to send. So this is a qubit. Then Alice will do something. And then send some 2 bits of information. Bob would do something, and we will get the qubit. Okay, so what does Alice do? So what Alice can do is she will take these two initial bits, and we'll apply a suitable unitary transformation B. Okay, so this is B is a unitary transformation that acts on the space of 2 qubits, and out will come 2 other qubits. Okay, and then she will measure these 2 qubits in the C basis. So she will measure sigma, the C component. Let me write bigger. Sigma C of the first qubit, and also sigma C of the second qubit. Okay, so that's these are 2 plus or minus. Those are 2 bits, and these are the 2 bits that she sends to Bob, and then Bob will take those 2 classical bits and will apply different, depending on the result of this measurement, he will apply different unitary transformations. Let me call them U. The unitary transformations depend on the result of these 2 measurements. So there are 4 possible unitary transformations that Bob will apply, and the result of this will be the qubit M. Okay. Now, we can wonder whether this always works or whether it works for any V. Well, in fact, it won't work for any V. So, for example, suppose you take a V which is the identity, then you measure these 2 things in the C basis, then you'll just will measure this qubit, and then you'll destroy the qubit. Okay, so it won't work for any V. So you have to choose this V cleverly, and this V has to have the following property. So one way to think about, so you can, we'll give an example, and normally these discussions are based on giving an example, but we can think conceptually what is the basic property that this V has to obey. And the basic property is that is the following. So V is a unitary transformation when we view it in this direction. So this is unitary in this direction. But what we want is that for any values of the measurement, we can view this tensor, so we can somehow rotate this V and take the input here that we have in M and view this line as an output line. This was one of the entangled qubits. And then for any of the values of the measurement, so any of the values of the sigma C, the requirement is that this V should be a unitary transformation from M to E. Okay? So that's what we want. So it's somewhat similar to these properties of perfect tensors that we saw in the Xidong's talk. It's not identical, but it's basically the same idea that there is a special tensor that can be viewed as unitary in different ways. Okay? So if V has that property, then we have effectively for each value of the measurement, we are giving, we can draw this diagram by somehow thinking of this as a unitary map that depends on these 2 variables between M and this entangled qubit, and then we can view the quantum information flowing through here, and then U would have to be, so let me call this unitary map B tilde, right? That depends on the classical bits. And then this U has to simply be the inverse of V tilde, right? So U should be just U, which depends on the classical bits, should just be the inverse of this unitary matrix. And then in that way, we recover the original qubit. Okay? So that's standard teleportation. Now, you can check that if you have a map, so as an exercise, you can check that this following map, the map from here to plus, 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 minus, minus. So that this type of map is indeed fine. So, and then, so this is a map that works. Okay, so that is an example. Okay, so that's the end of the discussion of classical teleportation. So in teleportation, we really, after we teleport, we just used this qubit. We cannot use it again for sending another one. Okay, so it's a resource we had to spend, and we cannot use it to send another one. Okay, so.
So yes, a very basic question.
Yeah.
You say classical teleportation. There is not sending a light wave with some.
Well, these 2 bits, you can send them in any way you want. You can send them by sending a light wave, by sending a gravity wave, whatever you want. Of course, a light wave would be most practical. But anyway, you can send it through the internet. I don't know. So any way you want to send it. No. This is quantum. This is bit. This is just the thing you send through the internet. This is something, I mean, first you have to share, so these two, to share this qubit, you need to do something sophisticated. So maybe you send this qubit through a very, very, very good waveguide and through entangled photons or something like this, or you put the spin in a Dewar and one of the spins in a Dewar and you take it to the other place. So it is hard to, well, presently it's somewhat difficult to send these qubits over long distances, but it can be done. Sending the classical bits is easier, so you just send them through the internet. Okay, so now, okay, so that's ordinary teleportation. So now I'll remind you of something which so now we'll use the relationship. So now we go back to black holes, so we'll consider the eternal Schwarzschild black hole in ADS, for example, which has a Penrose diagram roughly like this, well, where there is a left side and there is a right side. Better put the right this way. There is a left side and there is a right side, and then of course there is a future and past interiors. There might be singularities here somewhere. I'm not drawing the singularities. And the idea is that this type of state should be viewed, this geometry should be viewed as the thermofield double of the microstates of the black hole. So here we have the states on the left and the states on the right. And usually we should put a bar here, meaning that this is the CPT conjugate of the state. So if this has some complex phases, this is the complex conjugate, so the phases cancel. So that's the thermofield double. So the right-hand side is some construction which we can make whenever we have access to the microstate. So we have a full description of the microstates of the black hole, for example, through ADS-CFT or something like that. We can find the Hilbert space where the microstates live. Then we have a bunch of energy levels, and then we can do this construction. And the idea is that this should be true for any black hole as long as we have access to the microstates and we can describe them explicitly. Well, even if we cannot describe them, if they exist, then the eternal black hole should be described by this type of construction. So here, the idea is that, so this is a very entangled state because, well, we have this correlated sum over n, and the entanglement entropy of the thermofield double, so S entanglement. So if we look only on the right side, you can look at the von Neumann entropy or entanglement entropy of the right side, and that will be equal to the black hole entropy. Okay. And in other words, even the full density matrix on the right is just simply e to the minus beta h, where this is now a density matrix that lives purely in the right Hilbert space. Okay. Okay, good. And the idea is that with this large amount of entanglement, and in this particular state, we create this connected geometry. So here the geometry is connected, but we don't have a direct interaction, even though we don't have a direct interaction between the two sides. So if you have an entangled state, you cannot send information by just acting on one of the sides of the entangled state. Right? So if we act here on the left with some operator, we'll create a signal, and the signal will go this way, and we will not be able to see it from the right side. So the density matrix on the right will continue to be the density matrix we had there, independently of what we do on the left side. But we see we can almost send it, right? It's just behind the horizon. Now, you might worry that maybe there is some correction, some gravitational correction or whatever, that moves this signal a little bit to the right. That would be enough. So a very tiny correction would be enough for you to send the signal. So you have to make sure that the simplest corrections do not allow you to send the signal. Or maybe it could be that there is some quantum correction to the solution that maybe opens up the wormhole a little bit, and then you can send the signal. Now, you might wonder that perhaps you can send some particle here, there is some scattering, and then this has a little bit of then this can be scattered to the other side. But it turns out that, well, simply the causality of the scattering in this region ensures that this cannot happen. And also, there is the average null energy condition, which I guess Tom Faulkner described a lot, ensures that you cannot have traversable wormholes. So wormholes which contain two disconnected regions like this are solutions of general relativity, so quantum effects cannot give rise to wormholes where you can send a signal from one side to the other. So if you have in general relativity, if you have two disconnected asymptotic regions, you cannot send the signal from one to the other. And all this relies on the average null energy condition. Okay, which is the integral of t plus plus. This should be bigger or equal than 0. And this is something we expect to be valid in any sort of, well, it's proven in quantum field theories in flat space. I'm told the proof might generalize to this case, and that sounds reasonable, but at least it hasn't been written, as far as I know. And then it's a property that we expect to hold in general for so-called achronal lines. So lines that are the fastest line in the space-time, so that there are no 2 points along the line, along this null line, that are time-like separated. So there are examples where this condition doesn't hold. So for example, if you take a cylinder in 2D quantum field theory, you know that the Casimir energy on the cylinder is negative. And so if you take a line that goes around the cylinder this way, you will get something negative. But this line is not achronal. So there is these 2 points, for example, are time-like separated. Okay. So this is some condition that's supposed to hold for so-called achronal line. So it should be called A neg. Okay, so it seems that general relativity then has there is some interesting relationship between the positivity of energy and causality, and it ensures that this interpretation is always reasonable. Okay, so with all that said, there are some interesting things we can do. So if we have, imagine that those two black holes are dual to some system that we have in the lab. So here we have a left a sphere with many qubits in the lab, and here we have some other sphere with many qubits in the lab. And so they exist, let's say, in two neighboring quantum computers, for example, or within the same quantum computer. We are so powerful that we can simulate a system that can have a gravity dual, and we can put them in an entangled state, and so we can have them in this particular state. So if we can do that, then we can certainly, in this context, put a coupling between the two sides, right? So once we have the system in that state, there is nothing forbidding us from putting a coupling between the two sides. So in the gravity description, that will look like will look as follows. So that will look, so we could, let's say it's a coupling we turn on at time equal to 0. So let's say there is some operator here, O left, and some operator O right, and at time equal to 0, we turn on this coupling. So we have e to the I g. We add to the evolution the unitary operator that describes the evolution. We add a term that contains a coupling between the left and the right systems at time equal to 0. Okay. So if it, yeah.
So how do you implement this operation? Because this is very non-local. You need to kind of bring the two sides of the wormhole together to make this joint operation.
Yeah. So the idea here is you view this in the context of ADS-CFT, where this wormhole is the dual description of some system that you have in your lab. So in your lab, you have some system of entangled qubits and spins. They interact with each other and they create a complex state that has this gravity description, right? So gravity description exists in some other space, which is not our four-dimensional space, in the lab where these things exist, where these qubits exist. Yeah? So then you could bring them close, or there is this speed of light that is very fast compared to the time it takes to go through, well, compared to the time scales that govern the evolution of these qubits. So this Hamiltonian that describes these qubits has a typical time scale, and that time scale is relatively long compared to the time it takes for you to communicate between these two sides. So we arrange all this. We can arrange all these things. Okay. So then we can imagine applying this operator at coupling with an operator of this kind at equal to 0. For that, you can say, well, you take these two qubits and you make some small interaction between them. Okay. So this is how the interaction looks like in the laboratory system, right? Here, from the bulk point of view, this looks like a weird interaction. This looks like an interaction that, so you start here with this thermophile double state, and then at this point you add, this interaction indeed looks non-local in the bulk. So it, again, so in the bulk there will be a field, let me call it phi left, which is dual to the operator O left, and a field phi right is the same operator. So we have an interaction that looks like phi left at 0, and then, well, phi left time equal to 0, and phi right at time equal to 0 also. So here phi is a field that exists throughout the bulk, and phi, so here phi left means that we insert the field very close to the boundary, some field insertion, and then here also a field insertion very close to the boundary. Okay, so that's phi left. This is phi left, and this is phi right. So it is as if we took these two sides and we said, well, in some ambient space, they are very close, and we can add this interaction. So when we add this interaction, then this can indeed create negative null energy in the interior.
Yeah, I have actually a
yes,
question.
yes.
So if you really want to, say, teleport to
Yes.
somebody very far away,
Yes, yes,
and then to establish this kind of interaction,
yes.
will take at this speed of light.
Oh, yes.
Yeah, even though it looks like an instantaneous interaction.
Yeah. Well, so here I was motivating this from the laboratory system, where this will look like instantaneous. If I sometimes like to tell the story in terms of Romeo and Juliet and so on, where you might have heard the story if you didn't. But so if you want to do it with black holes in nature, so there is one black hole here and one black hole very far away, right? So something we could do is, let me remind me of this question after I talk about the teleportation version, because we can do that in the teleportation version, but not in the with this type of interaction. This interaction involves exchanging qubits back and forth between the two sides. Okay, and it requires somehow that this is embedded into some space where the speed, where we have very fast communication between this side and that side. Right, that's what this interaction requires. Ask me, remind me. Well, I tried to remember myself. But okay, so that's this story. And when you have this type of non-local, this type of interactions that looks non-local here in the bulk, you can indeed create negative energy. And one simple way to see this, imagine that you have a strip, right, with some field. And then now you close the strip into a cylinder, right? So if you did that, then you would create a negative energy on the cylinder, right? So the cylinder has some negative energy. This actually also has some negative Casimir energy, but the one in the cylinder is bigger. So here is an example where you can really see that if you put an interaction, in this case, that exists for all times between the two sides, you can decrease the energy. So this at least makes it reasonable. Now, a little more concretely, we can think, for example, we can take an example in flat space where we put an interaction that involves this this form between 2 points in flat space, just as an example. And then we can calculate t++. Let's say we are doing this in a 2D CFT, where t++ is d plus of phi, d plus of phi. And then we can calculate the expectation value of t++ to first order in G. And so that involves taking t++ and adding this interaction e to the ig times phi e to the minus ig phi, right? And to first order in G, all we get is a commutator between, so we get a G, and then a commutator of the phi left, phi right, times this d plus, d minus. And then this commutator, we further expand it, and we'll get some terms where, for example, there will be a term where the phi left gets a commutator with the d plus, right? Ig. Well, even before I start doing the calculation, you can see that, so this will give us something, but by adjusting the sign of G, we can get the energy to be negative, right? So will give us something, we'll get some answer whose sign depends on G. So the statement is that we can adjust the sign of G so as to get negative energy. And now if we look at it in more detail, there is a term that has to do with the commutator. And then there is a term, let's say phi right, d plus of phi. Plus then there is some other term which looks like this with left and right exchange. So this commutator, so for a free field, is just the propagate, so it says the causal propagator between the 2 points. So we have to have the ability of sending a signal. And then this is non-zero when we have correlations between left and d plus, right? So we can do this in a 2D field theory, and then we'll find, so if we, so if x plus is this direction, and x minus is this direction, then this will give us a delta of x plus. So this type of thing will be localized along these two lines, and we'll have something, let's say, positive here and negative here. So when you do the calculation. Or we could have the opposite depending on what G is. So here in this region, we have this negative energy wave. Yes? No, we're not. We're putting it at the point in the boundary. Now, you might worry that we are putting the field at the point. We can smear it a little bit. I mean, we can smear it over a region of order the radius of ADS or whatever. It's necessary to eliminate UV divergences in the bulk.
So in some sense, you are identifying the points here with here to make
Well, we need some kind of communication between this point and those points through this exterior, right? Through what lies beyond this boundary. So we are making a small connection between the two sides. Okay. And the one way to think about that is that you had this lab setup where these things were evolving in an isolated way for all this time, and at time equal to 0, you couple them a little bit. And then you decouple them again after time equal to 0. Yes?
So
yes?
we are doing something in the lab, and so basically we can do whatever we want in the lab. And
Yes.
these 2 points do not need to be close to the boundary, right?
Yeah, you can do whatever you want in the lab. No, indeed, they don't have to be close to the boundary. We could think about some other situations.
Yeah, but why do you want them to close to the boundary?
Well, because they are like simple. So the closer to the boundary, the simpler the operator is. So we're imagining that. So if you had a point here, you would have to do. Maybe this is a slightly more complex operator where we have to make some time average here of the simple operator. It might be a little more difficult to implement. So here the point is that even with the simplest operator, we'll be able to do something. So you can certainly do some more complicated things. It's just this is a simpler case. Okay, so now we'll analyze. Okay, so the idea is that here this could create some negative energy. So this is negative energy following in. And then when we send a signal, so you'll have this signal, and there will be some gravitational interaction between the signal and this negative energy wave. And that will, by the opposite of the, so ordinarily with positive energy you have time delays in gravitational scattering, but if you change the sign of the energy, you can get time advances, and the signal can come out on the other side of the black hole. Okay. Now, the fact that you can send the signal, so let me make one first point, is that the fact that you can send the signal from the left to the right is not surprising, given that we have coupled the left and the right. Okay. So the interesting thing the important thing of what I'm discussing here is not that you can send a signal, but the important thing is how the signal goes, how the signal travels from the left to the right. Okay. It travels not by coming here and going through this operator and then coming back out here, right? What the signal does is just travels through this wormhole. Okay.
One question.
Yeah.
Can you make closed time-like curves in this geometry with the attic violation?
No. No, as far as I know, and I don't expect that you should be able to do that, because from the boundary point of view, this is a perfectly legal time-ordered situation. Okay, so now we'll discuss how to. So yesterday we went on and on about ADS2 gravity, and this process has you can think about it in a simple way in this ADS2 gravity, and we'll be able to easily see various conceptual issues. So remember that we said that in ADS2 gravity we have this space, and then we had all the gravitational back reaction had to do with the motion of the boundary inside the rigid ADS2 space. So here we are adding this interaction, and we are going to think about this interaction in the way we were discussing yesterday. So we have, we can think of this as a phi left, phi right. And what we discussed yesterday is that we can isolate this boundary degree of freedom and think of this correlator as being a correlator in purely ADS space. And so we'll take when we insert this in the path integral, we can approximate this as e to the ig, the expectation value of phi left and phi right, where phi left and phi right are inserted here at these boundaries. But we will take into account the fact that the boundaries can move, right? And if the boundaries move, then these expectation values will change, but in a simple way. They will change. So in the formalism with the Schwarzian, it will change by some time reparametrization. Or if we think in terms of these two particles, so if you move them further apart, this correlator will decrease. Okay? So that's just a correlator in ADS2, and we evaluate it at the positions of these two boundaries. Now, so when we think about it this way, we can think of this as some effective potential, V, which is turned on only for time equal to 0, but it could be an attractive potential, and so it can give an inwards kick to these two trajectories, right? So for time equal to 0, we turn on this attractive force, and so we can make these trajectories move in a new way. I wonder if you can see color chokes. Let me try with the red. So can you see this one? Maybe you couldn't see the other one. So could you see the white one? So this is the new trajectory after we gave this inward kick. So after we took into account the effects of this interaction. And so clearly, we need to choose the sign of G appropriately. If we change the sign of G, it moves them outwards, and it's not helpful for what we want to do. And then if we send the signal from here, we see that it can now reach the right side. Okay.
Sorry. This notation, this V, is meant to be the same as the V in the first lateral?
No, not quite. No, so yeah, this is probably not a good notation. So okay, let me. This is some B. Okay. I'm going to talk about the V in the next blackboard just right now, maybe. But this is not yet the same as the story there. So because in the story there, we're only sending classical information between the left and the right, while here we need to set up this quantum interaction. So quantum interaction means sending quantum information between the two sides. So in order to make it more similar to teleportation, we are going to modify this slightly. So we are going to, instead of doing this, we're going to measure phi left. Okay, so we're going to measure the value of the field here, and then the interaction we are going to be turning on is so let's say that the measurement of phi left gives us sigma left. So sigma left, so phi left is a quantum operator, and sigma left is a classical answer, which is the result of the measurement. And so we have sigma left. So now we are going to insert the interaction sigma left times phi right. Okay, so phi right is now an operator that will act on the right, and will do something. So this is the expectation value of phi right in the state projected by the result of the measurement sigma. Okay.
Professor, sorry, maybe on the gravity side, so the effect of this interaction is that you will source the dilaton, so the dilaton then will.
Yeah. There are different ways. There are different ways to think about this. There were 3 descriptions that we had for the gravity theory. So you're asking me about the dilaton description. So in that case, what happens is that you are sending in a negative energy wave, right? And what will happen is this will source a dilaton that will move so that the region where the dilaton had value phi b, the boundary value was this one, and this will change it so that the new dilaton will have boundary value phi b along this line. Okay, that's the description in that language. Here I gave the description in the language of the 2 boundary particles that are moving in a rigid ADS2. And then also we could use this Schwarzian-like description where we would, so in the Schwarzian-like description, this would give a new source term for the Schwarzian, which is of the form, let's say, f prime at the left 0, and f prime at the right 0 over, well, the 2-point function, basically. all to the 2 delta, and then we expand to first order in F, and this gives a coupling, and then we can solve the. So we were solving the original Schwarzschild equations. We're given this answer, some original answer, and this will source some first order deviation for the Schwarzschild. So that's so we can expand F as the solution, the original solution for the thermofield double, plus some small deviation.
So from the digital picture,
yeah.
both horizon and the boundary shift, right?
Well, in the dilaton picture, the position of the horizon is determined by where the phi b, the curve of constant phi b intersects the boundary of ADS, right? And so then the new horizon is here. So in the picture with the dilaton also we have a rigid ADS2 space. So in all pictures we have a rigid ADS2 space and something that's going on. So here in the dilaton picture we have the dilaton changing and so on. This is, yeah.
Does it make a difference whether this operator is relevant or irrelevant?
No, it doesn't make a big difference. What you want is an operator which has high correlate. The correlation should be relatively high, right? And so if this 2-point function is very small, this force that will feel will be very small. And so you want to set up a situation where this correlation is relatively large. So for that, it's better to take an operator and average over some thermal scale, or take many operators and so on.
Question.
Yeah.
So when you say mirror this phi L, you are like working in the gravity side, right?
Yes.
But like when we try to implement like this E
Yeah, we could do it in both cases. We could, yeah. So measure phi L, or in the boundary theory, measure OL, right? And sigma L is just the result of that measurement, right? So we could do it on the field theory side or in the gravity side. We are just measuring that, and we'll get some classical answer, and that's the same in both sides of the duality, right? Okay, so this is an alternative way of doing things. And now, in order to figure out what happens if you do this, one thing we can notice is that if we follow the original description and we made the measurement just immediately after, then so immediately after the left and right sides are not coupled anymore, right? So if you do the measurement just immediately after, whatever the right person sees should not be changed, okay? So that means that the signal will have to go through and reach the right guy independently of whether we follow the first procedure or the second procedure. But I mean, this field is somehow evolving somewhat slowly. So if we measure it just immediately after, that's the same as doing the original procedure. So that's some argument. So the end point is that if you do this measurement, so here you measure sigma left, you will affect what this left side does. And indeed, doing the measurement, you will send in some positive energy. So here, when you do the measurement, you will send some positive energy this way. So before we were sending negative energy. So this side of the line is changed, and now this side of the line will do something more like that, well, because we did the measurement. But we use the result of the measurement to somehow extract something from the black hole, right? So here we had some correlations between the two sides of the black hole, and there are some fluctuations, and sometimes we have somehow some negative. If you wish, you can view them as if you knew what the field is going to do, you could add some terms in the Hamiltonian that extract some, for example, some energy of the black hole, or in this case, allow you to see a little bit behind the horizon. But you need to know what the field is going to do. And by measuring this correlated variable, you can know what the field is going to do. So, yeah. This is all like, it's a bit like insider trading, okay? So you know some information that is not publicly known here on the right side, but you can use it to your advantage and do something that you wouldn't be able to do otherwise. Yeah. Yeah.
This is the decoding operations made also by the
Good, yeah, so that now you can ask this question about the U and B, okay? So when we do this process, so the idea is that the V is the whole time evolution of this black hole here on the left side. So it's the composition, well, here we have a slightly more complicated entangled state, but let's ignore that. This V has the important property of mixing up this degree of freedom M with the entangled state. And here, that V is essentially the time evolution e to the it h left, so the Hamiltonian on the left, and t is the time between these two things. Okay. So if we want to do this with a small number of bits here, we need this particle to be very close to the horizon, right? So that means that this t has to be sufficiently large. If we want to do it with just 1 qubit, then this t has to be of the order of the scrambling time, so log n. Okay. So then this information is completely scrambled with all the rest of the black hole degrees of freedom, and then when we measure this guy, the important point is that when we do this measurement, this qubit has essentially no obvious information on this. We cannot recover the information here from a measurement of this qubit. Right? So that ensures that we don't destroy it. Yeah. Nevertheless, okay. Good. So now, in quantum teleportation, there is, there are some resources you need to spend and so on, and so you cannot teleport an infinite amount of information, right? And from what I said, it might seem that you can send here a lot of information to the right. I mean, once you open the wormhole, you could send anything here. But that's only because we ignore the back reaction. So when you send this information, there is some back reaction on what this line is doing. And if you include that back reaction, then there will be a limit on the information you can send. So, this Justine pictures looks as follows. So this diagram is going to get a little more busy, so let me erase some things. So if we try to send too much information, then this line will get a kick outwards, and will follow now a new trajectory like that, right? And by the time that the perturbation acts, or we do the measurement, then we will be far away from, we will be further away, and the correlations here will be smaller, right? They will be smaller, and the power of the wormhole will be a little smaller, and we will get a smaller kick here, a smaller inward kicks, and maybe we won't be able to see the information we're trying to send if it is too much. Now, yeah, all of this can be made a little bit more precise, and I won't show you all the formulas. You can find them in our paper. In the case of ADS2, in the case of ADS3, they were discussed in the original Gao, Jefferson wallpaper. But
there is naivety from this argument.
Yeah.
Say if you send it, say if you want to send more information.
Yeah.
But if you send it earlier, because there's a t equals infinity.
Yes. Yes.
And that will help you, right?
Yeah. That's right. So sending it earlier. From here, it will look like it will help you because it's closer to the horizon. That's absolutely right. But also, if you send it earlier, there is more time for this deviation to accumulate. So if you send it earlier, you will get a kick, and these two start diverging exponentially, and that kills you. So you cannot win by sending it earlier. So there is a kind of, there is a time where around the scrambling time, which is the optimal time to send information this way. If you send it too early, you can so if you send this too early, you still get some effect on the right, but it's a small effect of order 1. So even if you send, let's say, n qubits very early, you will get some little effect of order 1.
Yeah, something will leak.
Yeah. So the commutator between something very early and and so fields on the right will be of order 1 at late times, independently of how big G is and so on. So you can deduce that from the formulas. And here dynamics is so simple that you can take all that into account. I won't discuss it in detail. But basically, writing those formulas is just writing the math behind these pictures. So you can see that, well, you can believe me that the dynamics is so simple that you can write all these formulas. Let me just say a few more words about the bounds on information. So if you, here you create some amount of negative null energy, which is of the order of G and the amount of correlators that you have, right? And then the whole effect is, so I'm going to try to write down what delta x minus is. So so the effect of this shock wave, so let's say there is a negative energy shock wave, the effect of this shock wave on this particle. So I'm just going to follow the order of magnitude and n dependence. Then we have a g Newton, or 1 over n. And so in general, this will be, if we have a small number of fields, will be a small effect of order g Newton or 1 over n. We can make it a little more, we can make it bigger if we have k fields. And we make k relatively large. Okay. We could also enhance the effect by considering many Rindler modes or operators closer to the horizon. But just in this simplest setup, you would need to put many fields. And this is an option that you have, for example, in the SYK model, where you have n fermions that you could correlate between left and right. Now, the earlier you send this particle, even if this particle has an energy of order the temperature. So let's imagine you send an energy of order the temperature, but very early. Then the momentum in this flat space coordinates here in the center. So there is some x plus and x minus. And let's think about the flat space here in the center. We can do this even in ADS by considering the ADS charges as opposed to the flat space charges. But this momentum, if you send it very early, will be very high, right? So this P minus will be the form of e to the t, right? Okay, very good. And we wanted to send it early enough so that the momentum is sharply enough localized that the spread of the wave function is less than this delta x, right? So we want this momentum to be higher or of the order of 1 over delta x minus, okay? And so if we try to send n bits, so we have to, the total p minus will be this p minus that has to be at least this times n. So we are sending, let's say, n bits. So we'll have something which goes like n times this value of p minus, that it's the minimum value we need, and that is of the, yeah. Okay, so that's n delta x minus, 1 over delta x minus. Now it turns out that the corrections to this potential that we get between the two sides, so we had this potential for n bits, we have some potential which is roughly proportional to this. It decreases like 1 plus g Newton, the total p minus, right? So this is roughly related to the kick that this particle will give to the trajectory. And so in the end of the day, what we need in order for us not to suppress the interaction too much is that g Newton times this total p minus should be essentially less than 1. Okay. So that says that g Newton times g Newton times n times this 1 over delta x minus should be less than 1, right? And this delta x minus, I put it on the right-hand side and use this relationship. So we get g O k g Newton. The powers of g Newton cancel. And essentially, we have a bound which roughly says that the number of qubits we can send is bounded by the size of the correlators times the number of fields that we are using. So the total amount of correlation function that we have. So that's a rough bound of order of magnitude, simply deduced in this way. Okay. Now we've been discussing negative energy shocks and so on, and I now like to make. Well, let me first make one remark related to teleportation. So if we imagine we are describe the mechanism of teleportation through this figure, right? And someone tells us that they're going to teleport us, right? So they're going to take us, so this will be us, right? And then you will be put in a big machine that will mix you up completely with some entangled bits and convert you to classical bits and send you somewhere else, right? Would you agree to this procedure? Now, if instead they told you that you just have to simply jump into a black hole, and then you do the measurement here, and you just sail smoothly through this black hole. I mean, here, well, there's a picture where there's a shock wave, but there's a picture where all that happens is this. So you just sail smoothly, and you're rescued on the other side. So this looks a little less scary, less painful. And so you're more likely to agree to this other setup. So this way of saying it shows that why this process is a bit surprising, that you are exploring this interior of in some sense you are exploring a bit of the interior of the black hole, and you are making this geometric connection feel a little more real. Right? And this, you could in principle explore it. Of course, this is still a bit dangerous. If this person forgets to turn on this interaction, you fall into a singularity. So. Okay. Okay, so now I like to mention something that's not directly related to what we're discussing, but it often comes up in discussions. So imagine we have the thermophile double, right? Again, so this is a situation when we have these two isolated systems evolving according to unitary evolution. But imagine that we couple this system to some external reservoir, right? With some external system at 0 temperature. Then the black hole here can start evaporating and emitting energy to the right side, okay, to some other thing, other system. So this side of the black hole is cooling down. And so that means that in some sense there is some negative energy flowing into the black hole, right? Now this looks a little, this looks interesting because now it might seem that you can send, so you have some negative energy flowing in, and then you can send some particle from here, and the particle, due to this flow of negative energy, will jump out and go here to the right. Are you bothered by this or not? You should be bothered by this because these are two decoupled systems, right? And nothing you do here should affect what's going on here. So the fact that you couple this to some other system should be completely, well, it should be irrelevant in the sense that it should not help you in any way get the signal out. Okay? So there is something wrong in this argument.
Well, it's an entangled state, so it doesn't really follow if you think of feature of that CRT set. You do something here, so it's an entangled state, it will have some effect on the other side.
Well, let's imagine the lab again. So we have the left side and we have the right side. We have an entangled state, and then we cool down this this side of the entangled state, right? Can we send a signal? So then we do something to this. Can we receive a signal from this side into that side?
Might cool down. Like if you want to do some measurement on this side, then this side is also going to change accordingly.
Yes, you could do measurements here, but the point is we are not exchanging any signals between the two sides.
You have just changed the entanglement pattern, so now that
that part is entangled also with the external.
Yes. This will also be entangled with the external.
It's
Yes.
inside another kind of wormhole.
Yeah. There will be some wormholes that connect here to the radiation and so on. But the question still is, so we have the right system. The right system couples to a big thing at 0 temperature. So part of the qubits from here, the information from here goes into the big system. But then this system could be very far away, right? The system could be like some other galaxy. I do something here. Do I ever see anything here on the right? In principle, the laws of entanglement tell us we cannot send any information by doing any of this. So then there must be something wrong about this gravity argument that we send negative energy. And in fact, you can prove that in this context, the integral along dx plus t plus plus is actually bigger than 0. So this, if you approximate this by flat space, it's more or less clear that that's the flat space proof. No matter what I do here, we'll just get this to be positive. And you can also do the proof here in free field theory. You can show that this explicitly that this is a positive operator by doing some kind of Lycon quantization along this line. Okay, so we conclude that this should be positive. So this energy somehow should be positive. We have this negative energy. And the key is that at some point we had to turn on a coupling, right? So we have, let's say we have some field. We have some coupling that depends on time. We have the field of the right CFT. And we have some operator, let's say U, that lives in the reservoir, right? Or this system at 0 temperature. And this coupling was 0 at early times, and then we turn it on, right? Now, when we turn on the coupling, we send in, we can send in some positive energy. All these were negative energy. And what happens is that this positive energy contributes more to this than all this negative energy combined. Now, how can this be? Because this seems to be going on for a long time. I mean, it could go on for a long time. And the key is that we are talking about when we let this, we should distinguish clearly between this energy and the Schwarzschild energy, or the energy that we measure in the boundary theory, which is basically computed by integrating dx plus t plus plus times x plus. Okay. So by doing this coupling, we will get a constant rate of this energy out. But notice that for larger x pluses, so these larger x pluses, the necessary contribution of t plus plus is smaller and smaller, right? While this one came very early on, when x plus was very small, was relatively small. So even though this is a very small contribution to this kind of energy, so the usual energy in the field theory, it is a bigger contribution and bigger than all of the rest for this null energy that is the one relevant for teleportation, relevant for traversability. So this energy is the generator dual to boosts, right? This is the boost energy, and this is just simply the P plus energy in this flat space coordinates. These are two different notions of energy. The one that is negative and with a constant rate is this one, and this one is the one responsible for teleportation.
So this E is the boundary energy, right?
Yeah, that's the boundary energy, or in the bulk, it's just the boost energy. So the energy measured with respect to the time translation, approximate time translation killing vector.
So can I also just think that the first energy is the increased more under the boost than the later energies?
No, well, let me see. No, all this process is essentially a boosting variant. We can do this whole evaporation process earlier or later, right? That's what doing a boost would do, and that will not change this energy because it's.
The boundary energy does not change.
Yeah.
But the bulk energy, the relative bulk energy changes because the earlier signal have more time to be boosted in the bulk.
Well, yeah. So, well. We are talking about two different notions of energy. This is like boost energy, and this is translation energy, ordinary translation,
So this
P
is
plus.
translation energy on the bulk?
Yeah, in the bulk side, yeah. So this doesn't have an obvious boundary statement, right? There is no symmetry. So this energy is not associated to any symmetry, right? We don't have an X plus translation symmetry in this picture. We have some kind of approximate translation symmetry along this surface, but in the neighborhood of this surface, but we don't have it in the full space-time. So it does not translate to an actual symmetry of the boundary theory. The boundary theory is only invariant under the boost symmetry. Okay.
Is this argument depending on the sign of G?
No. Whatever is the sign of G that you turn on here, because for any sign of G that you turn on, any coupling, you will have some energy leaking out into the reservoir that is at 0 temperature. And so here you'll always have this pulse of energy. I mean, the way you know it should work is that you can write this in field theory as a positive operator. But it's an interesting exercise to do this explicitly and see that it does work. I mean, you just do the calculation.
You can just use the argument that you used earlier, right?
Yeah.
Look at the expectation value of that guy.
Yeah.
That must be quadratic in G. Because phi can only contract with itself.
Yes, that's right. Okay, good. So are there any other comments or questions? Okay, so now I'd like to discuss the relationship between this story and this Hayden-Preskill discussion. So, first I'll try to remind you what the Hayden-Preskill paper said, and then we'll discuss it. Okay, so Kitaev talked a bit about the Hayden-Preskill. Let's say we could call it a paradox or a surprising property of black holes, which is the following. So imagine that you have a black hole, okay? And there is this guy Bob that has been observing the black hole for a long time, and so this is Bob, and he has a system in his quantum computer. So this is a quantum computer, and the black hole is perfectly entangled with the quantum computer. So he has, in some sense, a kind of copy of the state of the black hole in the quantum computer. Then Alice comes along and sends her diary, or let's say a message, this is Alice, into the black hole. Okay. Then the idea is that Bob collects some of the Hawking radiation from this black hole, so some Hawking radiation, and then feeds it into his quantum computer and does some operation, and out comes Alice's diary. Okay? And the basic point of this is that Bob does not have to wait for the whole black hole evaporation or anything. He has just to collect enough Hawking radiation. The number of qubits or bits that he needs to collect here is of the same order as the number of bits here in the diary, including the rest energy of the diary. Okay, so this is something that they argued basically from basically roughly like this. So you have the black hole, right? These are the black hole degrees of freedom, the initial black hole degrees of freedom. This is the diary, and here we're imagining that you entangle the diary with some reference system, and so these are similar to the drawings that Kitaev gave in his talk. So we have then the time evolution. So we have that when this falls into a black hole, there is some kind of time evolution for a little while. This is somewhat like the V. And then we have, I'm going to switch here. So we have the final black hole prime, and then we have some Hawking radiation. And then we have this also reference system in the quantum computer that Bob has. So the idea is that if this Hawking radiation, the dimension of this is slightly bigger than m, then the dimension of this whole system is going to be bigger than the dimension of this system. And it sounds kind of reasonable from the page type argument that if you have, the page argument says that if you have something which is less than half the system, the density matrix here will be just an identity. Okay? And that means that R will not be entangled with the black hole degrees of freedom, so that R should really be entangled with something here. And so we should, in principle, be able to distill the information. We should be able to find the qubits that are entangled with R, and that's the diary that was contained in the message. So that makes it plausible, but you can also argue, and Hayden and Preskel do in their paper, that if you assume B is sufficiently generic or unscrambling, you can indeed do that. Okay. So I won't discuss why you can do that. But this fact led them to think that there might be a paradox, because you have, let's say, you have the black holes. This is Alice's black hole. So the black hole, and this is the exterior of the black hole. And so then Alice could sense the diary. So the diary somewhere went inside. And then they were imagining that Bob here comes and, so he had Bob's quantum computer here. And Bob collects some Hawking radiation here that will contain the information of the diary. And then after he decodes the information, he can jump into the black hole and actually see the diary. Or you can arrange for the diary to send some signal. This is sent into a spacecraft that at the right time it ejects the diary in this direction and sends it so that Bob can see it when he falls into the black hole. Okay. So then Bob would see this information twice, and it would violate the no cloning of information. Now, they noticed that due to the fact that here you have to wait a scrambling time, so a log n time, in order for things to thermalize enough so that there is no information there is no information of the diary remaining here. Then that implies that there is a large boost factor between Bob falling in here and this diary, and so in order for Bob to receive the diary, this has to be sent with energy which is bigger than the Planck scale. Okay. And so here it looks like you could not do that, but due to Transplanckian, it would involve a Transplanckian transaction, and so we don't know whether we can or cannot do that. And so it sounds like, well, this extraction of information and so on is protected from contradictions by because it somehow occurs beyond the reach of the law, beyond the reach of ordinary gravity. Okay, so now we'll analyze the same problem in light of what we've been discussing, and see that the two things are intimately connected, so that the extraction of the diary and so on, we can view it as intimately connected to teleportation. So Hayden and Preskel didn't give us a precise algorithm for doing this, but we'll just say that, so this was Alice's black hole, and let's say that Bob, in his quantum computer, produces the thermofield double. So it simulates the Alice's black hole, and in a completely identical copy, and gets the whole state in the thermofield double. So the left side is Alice's black hole, and the right side lives in Bob's quantum computer. Okay. So now the space-time diagram that we draw is this one, the same that we were drawing before. And so here Alice sends the diary, so that's M is the message or the diary that Alice sends. Then Bob somehow reaches out here and collects some Hawking radiation from here. That is equivalent to doing, could be viewed as doing a classical measurement, or he could even get the quantum qubits, and then feeds them into his quantum computer and does something. And the something he does is precisely what we were doing. What he needs to do is precisely adding the interaction we were talking about, right? And once he does that, the message comes out, right? So then he can recover the message, so that there's this new evolution, and recovers the message out here. Okay. Okay. So that's the story. That's how Bob recovered the message, and then Bob can now jump in, and if he wants, he can or cannot take the message with him. But the message is somehow, the message here in the bulk is only in one place, right? So we never have the message in two places. So here, this space-time picture suggested that the message is both here and in the Hawking radiation, right? Both here and outside. But here, when Bob does this of extracting the message, so now the message is not anymore in the geometry, right? And so Bob jumps in and, well, can do whatever he wants. So the whole process occurs according to the laws of general relativity in the bulk, and you don't need to involve some Transplanckian story or anything like that. If Alice arranges so that the message gets ejected in this direction, right? Then, so Bob here will find the empty rocket, but will not find the message, right? And then when he goes in here, he will see the message, but he will not have the original message. There are some things Bob can do here, like extracting the empty rocket and evolving the system backwards in time to extract the message. And then if you do that, then when you evolve then this forwards in time, the message will not be there, and when you fall in here, he again will not see the message. So everything is legal according to the bulk point of view.
From this point of view, there's no possibility for the second possibility, right? Because the Bob will always get the message.
So here we discuss one possibility, which is that the message just goes in, right? Yeah. And Bob decodes it, right?
Yeah, but Bob will always get the message.
Yeah. Well, I guess if Alice arranges for the message to be sent this way, right? Then when Bob tries to do this decoding operation, at this point he will not find the message. He will find an empty rocket without the message.
But from this
yeah, from this perspective.
It doesn't matter whether Alice arranged the message in what way. Bob will always get the message.
Yeah. Here it looks. Yeah. I see what you're saying. Yeah. So but the thing is, here it says that Bob in principle can get the message, right? What he has to do, this argument does not specify. So if Bob does the simplest operation that I was discussing here, he will not get the message. He can get the message, and according to the general theory, and what he needs to do is the following. So there is the empty rocket here, right? At this point, he takes out the empty rocket from the space-time, and then evolves the system backwards in time, okay? Then this message is now evolved backwards in time. There is no rocket coming in from here. This occurs in a new sheet of this space-time, right? Yeah. Where there is no rocket, and then the message comes back, and he gets it here, right? He could then evolve this forwards, and then we'll get a new sheet of space-time without a message or a rocket or anything, and then he could fall in that new sheet of the space-time.
Yeah, but somehow the thing is that here, Bob doesn't have to do those complicated things. He always just gets the message.
Well, the thing is that he has to do something. Well, here we are not specifying what he has to do. This is a formal argument that he can in principle do it. This argument doesn't tell you what you need to do, right?
You say that setup can give you much finer.
Yeah, this is a simple thing that you can do. And if Bob sets this up and Alice doesn't do anything funny, he will get the message. If she does something funny, then it will take more work for him to get the message. So Kitaev discussed something you could do basically for recovering this information, but it was much more complicated than this. It involved evolving backwards and forwards the system. And the advantage of that argument was that it worked more generally. This works. Yeah.
So and then you say actually there's no paradox at all. You don't need to hear this.
Yes. Yeah. The point is the following: that once you draw the proper space-time picture, right, you find that actually Bob's quantum computer is connected to the interior. This is something that wasn't in the original papers, the original Hayden Preskill paper, and so that's the new point I'm making here.
So there's absolute no danger you will get the two copies.
Yeah, because the basic point is that the process of Bob decoding the information reaches out and pulls out the message from the interior, right? So it's the fact that things can go through wormholes, and that, I mean, this is also connect, yeah.
There was this old argument that it would take a long time to decode.
Yeah, so here, yeah.
But you have here a very short time.
Yes. So here I made a small cheat when I was talking about this, which was when I said that Bob can produce the thermofield double, right? So this is something that would be very difficult and probably would take a very long time. So for Bob to make the thermofield double of the black hole. He could do that before Alice sends the diary, or he could. This was also assumed in the Kitaev discussion.
But Kitaev talked about the Grover.
Yeah, but the Grover search was something that you do after you already. He had the black hole and the entangled system in a simple state, equivalent to the thermofield double. So he also.
That in order for Bob to acquire information from the
Yeah.
which in your picture is just
Yeah. Let me try to. Yeah. Let me try to say.
discussions, it looks like it's very long.
Yeah. Let me try to say the difference between what I said and Kitaev. So. In both cases, we assume that we have the black hole entangled in a simple way with the quantum computer. And this is very difficult. So you have a purification of the black hole states. And you know it. So this is very difficult. Okay.
This is a time-dependent purification, no? So it's going to, so the black hole will
Yes.
understand it as evolving in time, so it's...
Yeah, you can. Yeah, that's right. But let's say we imagine that we have it at equal to 0, right? So at equal to 0, then now we have, this qubit is entangled with this one is entangled with this one. So every qubit here is entangled with a simple qubit on the right side. So in that sense, we've purified the system in a simple way. So we can represent it by something with more or less roughly like this line here. Okay. So both discussions were the same. Kitaev assumed that this V was a generic unitary. Okay. But well, with some finite number of gates. Here we assume that the unitary is somehow special. It's the one that corresponds to evolution by roughly a scrambling time. So Kitaev's discussion would apply when that evolution is much bigger, let's say, than the scrambling time. Okay. Then I was telling you before that if you wait for much longer than the scrambling time, you don't send, at least according to the simple protocol, you don't send much information. What Kitaev showed was how to go backward, do this backwards and forwards, use this Grover algorithm and so on to enhance these little few qubits that we were sending and produce the whole message back, which the general argument said that we should be able to do. So that's the difference.
You mean that in the Kitaev's case, your wormhole is longer and you have to shorten it to
Yeah, that's right. So somehow in this picture that we were drawing, so we had the initial boundary trajectories, right? And you send something really early, and so the new boundary trajectory is really very, very, very far away, right? And so you need to somehow, when you ball backwards and forwards, you start getting quantum superpositions of all these trajectories. And I don't know the gravity picture of that, but I think roughly you start getting quantum superpositions until you, you make the thing appear. You enhance the probability that you'll get the full signal back. Would be nice to find the gravity picture of what he's talking about. Okay. Let me see. All legal. Now, there is one more general point I wanted to make. Is that.
Sorry, you are saying in the
Yeah.
standard argument, when people doing this complementarity,
Yes.
and the UAs have this danger, have a chroning.
Yeah.
That just have no danger.
Yeah. Well, this is very connected to this discussion that Lenny and I had on the AMPS paradox, on the version of the entanglement for the AMPS paradox, and how wormholes can deal with it. So let me remind you of what that was. So the AMPS paradox is saying that we have some we have some black hole that is entangled with radiation, right? With some radiation or with some quantum computer or whatever. So we have some qubit here in the outgoing radiation, let's call it B, and that's entangled with, in the quantum computer, some other qubit that lives in the quantum. So this is a qubit in the quantum computer, right? So these two are entangled in the, let's say, maximally entangled state. Okay. Now, in order for the near horizon geometry to be smooth, this also has to be entangled with a degree of freedom that lives in the interior of the black hole, right? So you have to have this B maximally entangled with two things, and that's impossible, right? So this looks like it's occurring on all in the same spatial slice, okay? But the point is that this point really is to the future of this one through the wormhole. So that's the point is the following. The point is that we can think, so we can, let's say when we purify this, we can purify all the qubits and get the thermofield double. So if we do that, then this left side now lives in, so this was the black hole. Unfortunately, I reversed the black hole and the quantum computer relative to the previous discussion. Hopefully that won't cause a problem. So this was the quantum computer, which now has been turned into a black hole. And now this qubit is entangled with some qubit B tilde here, okay? So these two are entangled, and so the proper space-time diagram is something like this. And now A is to the future of B, right? So there is no problem with B being entangled with B and the future copy of A. So this monogamy of entanglement is something that only holds when you have all three qubits living on some given spatial slice. But that's not the case. So the point here is that this is to the future of this through the wormhole. Okay?
So A essentially is the evolution of the B tilde.
Yeah, that's right. That's right. So that's the idea. So that I think is a solution of the first AMPS paradox, but it's not a solution of all the AMPS paradoxes. So in particular, because there is another objection to this idea is that, well, now that this A is in the future of this, you have to worry about something. You have to worry that if you do some change of the state here, so you could maybe have made an error in the purification, or you make, you can act with an arbitrary unitary here, and that would send shock waves to this place, and then could cause a firewall. So that was the response to this idea. But this would work only if you've first purified this and made the black hole really short, the wormhole really short, and then you send the shock wave. If somehow you had a bigger, longer wormhole, well, here and you did some, you did the same thing. This would come here, but not to this region over here. And so we don't know the proper solution of the paradox using these wormholes. It all depends on what the typical wormhole looks like, and we don't yet know that. I wanted to make one more point in this direction. Yeah, so they assume that, but we know this assumption is wrong, okay? I mean, if you accept this wormhole discussion, that assumption is wrong. What?
How do you know? What is the reason?
Oh, because B, so we could have, so they didn't say how you purify the system. But if we purified using the thermofield double, and you assume that the thermofield double gives this connected wormhole, in the connected wormhole, then A is in the future of B tilde.
But if this thing is the Hawking radiation,
If?
If this is not the thermofield double, but the Hawking radiation.
Right. So okay. So then the question is how that wormhole looks like.
Yeah.
So that wormhole could look in two different ways. So the right is always like this, right? That's the black hole. And then it might be a very long thing that splits into little tiny wormholes of the Hawking radiation, and each of these is one qubit, right? With a long region here, so that anything simple you do in the Hawking radiation might send something, but not behind the horizon. So that's possibility number 1. And possibility number 2 is that, all these Hawking radiation modes, they connect right behind the horizon, right? If you do any little simple operation here, you just modify what lies behind the horizon. So it depends on how the typical wormhole that connects to Hawking radiation looks like.
So, but we are saying somehow similar story as TOF, that the region 2 and region 1 is the same also.
They should?
Region 2 and region 1 is the same?
No. It's really different from what... So this identification, topological identification, makes doesn't appear here, and is inconsistent with what I'm saying here. So it's really something different. So he wants to, he doesn't talk about the thermophile double, but he wants to make an identification in the thermophile double state to view it as a pure state on one side. I'm never saying that. I mean, this is basically, once you accept that the thermophile double is the wormhole, I think you get this picture. It's not, you might reject that, or might say this is wrong, or whatever. But,
okay, you are not saying this, but it's the same information.
well, all we are saying is that this, so they assume that this is on a given spatial slice. All we're saying is that this A is to the future of this through the wormhole. So the proper causal relation is that that A is to the future of B through the wormhole. That's the proper causal diagram. If we do this purification. So now the story gets more complicated because the total causal diagram depends on what state this quantum computer is in. So this picture only holds for when we purify to the thermophile double. We could start doing other things. We could purify to the thermophile double and add a shock wave here, right? And then that's now a different story. So we have the shock wave, and we will disturb this. So now we'll have something different.
What is in the causal domain? What is the reason why Tilde is not like a little bit higher in the diagram?
Well, okay. So yeah. Let's. So when we have the thermophile double, so these are properties of the thermophile double that we're going to discuss. So forget anything about amps or whatever. So let's imagine a massless field that propagates in this geometry, right? So if we consider the left moving modes, right, we'll have some entanglement between these modes across the horizon, right? And so if we're looking at some mode B, right, this will be entangled with this whole line, right? We can call I was calling B tilde this one because it's sort of, there is an equal time slice that lies here, which is the boost of this time slice. So this is just the usual entanglement we discussed at the given time slice. And then we are just evolving this forwards in time. Okay, let me first do something simpler. So normally we say that a mode here is entangled with a mode here, right? Yeah, that's what we usually say. Now we were talking about some mode that lies here. So this can be boosted to this surface, right? So then we say that this mode here is entangled with the mode here. The fact that we have to move this backwards in time is related to the fact that when I talk about the thermophile double, I mentioned that we have to do E bar, so the time reversed, right? So this is entangled with someone here. But well, if these are just some, let's say, left moving particles, right? Of course, yeah, then the mode A is just the time evolution of this one. This is a simple picture. I mean, if you, in reality, there's a whole Hamiltonian evolution between all the modes here and all the modes this side. I was saying that B and A are the same, just as in the simple case that these are, let's say, massless fields. If not, it's a more complicated function, but still the fact that it is in the future ensures that they can be entangled.
So does this picture still hold if the wormhole is longer, like this deviation that we're describing?
This discussion? Yeah, the point is, well, I think the idea is that in order to purify, in order to find the dual of some mode that lives here, right? So if you have Hawking radiation, I suspect that the right picture is this one, that you have something like this. But now you want to take this Hawking radiation and find in this Hawking radiation one qubit, which is the one that purifies this one, right? What do you need to do that? So it's not clear, but it seems that maybe one way of doing this is to purify all of them and make this wormhole shorter and make it look like the thermophile double. That's what I was arguing before. But maybe you don't do that. Maybe you just leave something similar to this and actually find some qubit here, B tilde, and then you'll have a more complicated space diagram where here there will be a little tiny wormhole that connects from here to this B tilde, right? So you have space-time like this, and the process of purification will introduce some object here that. And so the idea is that the process of purification is not innocent. It can modify what lies in the interior. Okay. Now what they say is that the advocates for firewalls would say, well, given if you assume that that's true, that the process of purification can affect what lies in the interior, maybe anything you do can affect what lies in the interior. How do you know that just not doing anything doesn't have an effect behind the interior? So what they say is that if you do the thermophile double, then you have a smooth interior. That's a very special state. But for the generic state, we'll have some kind of firewall here. And you will, maybe if you want to talk about wormholes, you will have tiny wormholes connecting to the Hawking radiation. So this is picture number 2. So this is what advocates of firewall advocates would say. Okay. So they say, okay, well, okay, I buy this ER equal to VPR story, but the general picture will be like this. And we don't know which of the two pictures is the correct one.
But if you believe case that they're really maximally entangled,
yes.
then you can always build a good sumo field.
Yeah, you can always build it. Yeah.
And then that means that
yeah, but what they would say is that, okay, so you have this generically, and when you build it, you get back to this, right?
yeah, that's right.
And so when you build it, in both cases, when you build it, you get back to this. So what it is for the generic state is independent of the fact that when you build a nice state, you get this geometry.
Right. Yeah, but that means, but the Hawking radiation is maximally entangled.
Yes.
That
Yes.
means you always have that kind of situation.
No. Well, you have this situation only if you purify that Hawking radiation, you put it in a quantum computer, make a second black hole. Right?
Yeah, that's right. Yeah.
It's only that.
But
only
that's
there.
always doable.
It's doable, but the question is that whether you do it or not affects the outcome. Because even suppose you do this, right? Suppose the problem is that what you see here depends on what you actually did. So if you set up this black hole, okay, you see some smooth, nice thing. But you could also have done this and acted with a unitary transformation here, an extra unitary that sends a big shock wave here, and you will see it when you cross. Yeah. So that's. Now, some people like Rachua Papadodimas would say that, well, if you this state that has this extra unitary really should be viewed as equivalent as the vacuum, and so this is a slightly different idea. So there are many questions around this. So I by no means you think that these problems are completely understood, but there are some points that I think any solution should keep in mind. I want to say one more thing related to amps, and is the following. That so one of the amps arguments. Oh, I'm way over time. Well, maybe I say it very quickly. One of the amps argument was that so if we have the qubit that purifies B, right? Then so this idea that A is to the future of B tilde, right? Has apparently the following problem, that if you do an easy measurement, so you do any easy measurement on the radiation, then this commutator is expected to be non-zero, because there will be a complicated unitary between these two, and if you take any qubit and you make an arbitrary unitary transformation, then it will not commute with any other simple qubit. Okay. Now, the interesting thing is that this is precisely what happens in teleportation, but in teleportation it has an interesting, well, here I would like to write B here, and let's say we can think of B tilde as the signal we were sending before. So when we do this simple measurement here, it's somewhat analogous to this simple measurement here. And this measurement does not commute with the operator that created this qubit. Okay? That's generic, and it's true in all teleportation discussions. So even in this simple one that we started the discussion with, if you take a sigma matrix that acts here, it does not commute with those sigma matrices that we measured. Okay? We can see this on this picture by noticing that so this created some shock waves, and if we evolve them backwards in time, they will create some shock waves here. And so if we first, let's say, do this and create this particle, and then we act with this, and now we evolve the particle backwards in time, then the particle backwards in time, let's say, we get moved somewhere else and out of our reach, for example. This is a reflection of this large commutator, order 1 commutator. But in this space-time diagram, even though you have certainly a large commutator with the boundary operator, you don't have a large commutator with the bulk operator here, right? So we should distinguish this thing which was the original boundary operator from the thing that is the bulk degree of freedom here. And the bulk is really very smart because the bulk knows that this measurement did not destroy this qubit. So it destroyed it for the point of view for the observer on the left, but it's not destroyed for the one on the right. And the bulk knows that. It knows that this qubit can still be teleported through the bulk, right? And has not been destroyed. This is something that is not obvious in the usual diagrams that we draw in teleportation, that there is some place here where that qubit is. Well, you can think that this qubit is somehow in this line that we got by thinking about the unitary that way. But it's something that the bulk does somewhat automatically, at least in this setup. Now, so this is just a comment. I'm not sure what more to make out of this, but it's an interesting feature about this whole story. Okay, so yeah, I think I'm way over time, so I'm going to end here. Thank you.
Say again why you said at the beginning there's not commutator, but somehow when you go to the very close, the commutator becomes very small.
Yeah, so here I'm just using some kind of bulk theory, right? Yeah. So it's just the commutator in this field theory in the bulk without imposing the gravitational constraints that is small, in the sense that they are space-like separated in the bulk. If you wanted to refer it to the boundary, then there is a large commutator. But we could refer this one to the other boundary, and then there is one.
Because at the beginning they have like separated, that's why they have a large commutator.
Oh, why they had a large commutator? So that's because there was this scrambling transformation that was acting as a big random unitary. So if you have, let's say you have one sigma matrix, right? So let's say you have two qubits. Well, you have one sigma matrix here, and then you have sigma matrices on all the qubits. So let's say you take two initially commuting sigma matrices, the one at side 1 and the one at side 2. And now you act with a random matrix, right? So then the commutator between, let's say, sigma 1 and u sigma 2 u minus 1 will be of order 1. So yeah, so that's roughly because this sigma, yeah. Well, I mean, if you think of the whole Hilbert space, right? The sigma has +1 in, let's say, half of the dimensions and -1 in the other half. You make a big unitary, it all gets messed up. That's this picture. This is also an argument that was used in AMPS to suggest that if you do any small perturbation of Hawking radiation, you will affect the qubits in the interior. But we see that the relation is a little more subtle, and we need to understand it better. I'm not claiming I understand it. I only can draw these diagrams. But when we translate from the bulk to the boundary, we should be a little more clever, and all these things will have to be taken into account. Maybe with ideas of quantum error corrections, ideas of building tensor networks, including the time direction and so on. So that's part of what we could do in the future.
More questions? If not, let's thank Juan again.
Okay.